With a very familiar exothermic reaction which involves nitrogen gas, hydrogen gas, and then you have this sign here. What does this sign mean?
Reversible reaction.
Reversible reaction, and then you have the product NH3. What we are going to see in a lot of these reactions that we are studying about is that everything is in the same state. In fact, all problems that we are going to be getting in the topic of chemical kinetics, all of the reacting particles are going to be in the same state. What about this equation? Is it balanced?
No. You need to add a 3 before the H2.
Yes, go ahead, Siri, tell me.
So you put a 2
3 H2 then 2.
I put a 2 here.
Yeah,
and then a 3 behind H2.
And I put a 3 here.
Yeah.
And I put
Nothing
here.
There's already a 2.
Yeah, it's already a 2.
2.
Right, nothing here, yes. Okay, so now we have the balanced equation. Is the equation familiar to you? Do you know?
Yes.
Go ahead.
Yeah.
The production of ammonia gas, yes, but what it's called by
Haber's process?
right, the Haber process. Some people say the Haber process.
What is it actually? So is it Haber or Haber?
It's a proper name.
I believe it might, well, it's a German name, right?
Okay, so probably Haber.
Right, so yeah, it might be Haber process. This reaction here, can you tell from this information if the reaction is exothermic or endothermic from the information that we have? Can you tell? But from what we were looking at last class, what symbol do we have to put in to tell if it's exothermic or endothermic at the end?
Enthalpy, the theta.
Which is like what? Minus.
The minus and theta.
So if I put this now, no, not theta though, Siri.
Isn't it theta? Delta.
Delta.
Delta. Right.
Minus delta H, then that tells me
Exothermic.
it's exothermic, that the system has lost heat energy to the surroundings. And we had our diagram like this to symbolize the exothermic process. Okay. Today I'm going to leave this aside. We also had some talk about the Boltzmann distribution curve last class.
Yes.
Right? This is T1 and this is T2. Which is the higher temperature here in this thing? T1 or T2?
T2. Because the kinetic energy is more in T2 and the temperature is the average of kinetic energy.
Right. This is not potential energy, this is number of molecules.
Yeah.
Okay? So when you see a peak here at T1 in the Boltzmann curve, that means a lot of particles have low energy. At T2, a lot of particles have higher energy. Okay? And particles on this side have a bigger barrier, a smaller barrier to cross to get over to that side. This one's got a bigger barrier. So all of that we've got there. But today I want to show you guys how we're going to use a strategy to predict easily what's going to happen in a chemical reaction. First, I'm going to show you when we change concentration. And that's pretty simple. I think it's logical that if I increase the concentration of these two chemicals on this side, what's going to happen with this reaction?
It would be an increase in.
Which side would be faster?
If
I increase the concentration of nitrogen and hydrogen.
The forward reaction, because there's more product being produced.
Right, the forward reaction. If I started removing this, if this is the Haber process that's going on in a big chamber, and then I have a tube that somehow collects all of the ammonia and puts it in another tank, what would that cause? So I'm making this less.
Right. So wouldn't it favor the reverse reaction?
It would favor the reverse, you think? Anybody else?
Can you repeat your question?
If I start getting rid of this from the reaction container, what would it do? Would it make the reaction come forward or go reverse?
Forward.
Alright, Manan, why you say forward?
So because if we remove the NH3, it won't go back. The reversible reaction won't occur, so only the forward will keep on occurring.
Why wouldn't it occur?
So because we are taking out the NH3.
You're taking it out. In other words, you're making this higher than this.
Yeah.
So if you increase the concentration on any one side, then the reaction behaves to kind of balance that off. Because then it tries to go the other side. Okay? And if you decrease the concentration on this side, then the reaction decides to fill that up by coming forward. Is that okay? If you're making this less, the system will come forward.
Yeah.
If you're making this more, the system will also go forward. If you're making this more, the system will go that way. If you're making this less, the system will still go that way. So, with this concentration, let's say we do this here. It's well known, it's in our textbook, it's actually part of chapter 5 that we have to, not chapter 5, chapter 7 that we have to apply. The Chatelier's principle, which says that if a system is equilibrium, like this here is in equilibrium when this and this, they've been formed and the forward and the reverse reactions are equal. But if it's in equilibrium and then we disturb the equilibrium, then the system behaves in a certain way. So if we put the concentration of the reactants higher, then the reaction will go towards the products. If we put the products higher, then the reaction will go towards the reactants. If we make the reactants lower, then it will come to make them higher. The system will behave to try to make it higher if we make it lower. If we make this lower, the system will behave to try to make it forward. So in anything that we do to the system behaves to do the opposite, to bring it back to some kind of balance. That's the Chatelier's principle. Now, I'm not going to write it out, you just look it up wherever you need to. And it says that if a system in equilibrium, and when we say equilibrium, we really mean chemical equilibrium, which I explained last time. Chemical equilibrium does not mean that these things have to be equal.
The rate.
Yes, Abhidya?
The rate of the reaction.
The rate of the forward process and the rate of the reverse process are equal. So the amount of this it's not changing, and the amount of this is not changing. Okay? But if that's the case and we decide to make this suddenly higher, then the system would start going forward like this.
Yeah.
And if we decide to make this lower, the system would go this way. And if we make this higher, the system would come this way. And if we make this lower, the system will go that way. So the system behaves in a way to oppose whatever we do to it. Okay? So that's with concentration. If you increase the concentration on this side, it's pretty easy to understand that. Now what about with temperature? This type of reaction here, what is it? Exothermic or endothermic?
Exothermic.
It's exothermic. Now, last class I was explaining to you guys about the size of the barrier and all of those things, right? You fully remember that discussion? And it's there on the video for those who missed it. You guys should watch that video. That's part of what this class has covered. But right now I don't want you guys to bother too much about the barrier and the size of the barrier as we go from reactants to products and then from products to reactants. Just like what I just mentioned here with concentration, I want us to think about exothermic and endothermic when we get that, in terms of like if they are chemicals. So here's how we're going to look at it. If heat is produced in this reaction, it's given off, which side of the equation should we put it on if we're going to like treat it as a chemical? We want to treat heat as though it's a chemical to make the process of reasoning easy. Which side should we put the heat on?
Both.
This side or that side? Both, you think?
Both.
Anybody else?
I didn't understand what you said.
You have nitrogen and hydrogen and they give ammonia, right?
Right.
Now we understand. Tell me if you understand. If I increase nitrogen, the system will start producing a little bit more ammonia. If I increase hydrogen, the system will still start producing a little bit more ammonia. If I decrease ammonia, the system would still
Produce more.
If I give more ammonia,
The
system would come this side. If I give less of any of these, the system will come this way. So the system tries to kind of fix whatever problem I caused then. With the equilibrium, if you think about it. The balance is there, right? And once I do something to disrupt that balance by increasing this, the system will try to go this way. If I decrease this, the system will try to fill it in. So if a system in equilibrium, chemical equilibrium, is subjected to a change, it looks to reverse that change or to balance it off. And the easiest way to understand it is with concentration. You guys are having any problem in understanding with concentration? No. Alright. So now because concentration is such an easy one to get, is it easy for you to get? I know. Right. Asna, you're getting it?
Yes.
Concentration is an easy one to get. We decided instead of talking about heat with all of this stuff here, that we are going to start treating heat as though it's a reactant. So if we had to treat heat as though it were a reactant, where would we put it? It's produced in the reaction, it's given off, right? Because it's given off, then we will put it
In the reactants.
In the reactants.
No, if it's given off.
It's given off.
Product.
No, so we will put it on the product side.
Product side.
So an exothermic reaction, we are putting heat as a product.
Okay. Yeah.
Yeah.
Okay? And then if we have the reverse of an exothermic reaction, which is an endothermic reaction, let's just put one like this. A plus B plus heat to give C. This one would be endothermic. So every time we have an exothermic reaction, which is negative delta H, and we have an endothermic reaction that is positive delta H.
And it's on a case and heat.
Right. Right. This one gives off heat, so it's like heat is a product. Okay? And this is not reacting in the chemical reaction. It's just a strategy that we're going to use so that you guys could solve certain kinds of questions very easily when you apply this strategy, right? And then this is an endothermic one here. So here now if I say in this reaction, following the same principle, right? If heat is a product, if I increase temperature and I give more heat, what would the system do?
Produce heat.
So could you repeat?
If I increase temperature by giving more heat,
Okay,
what-
so like in terms of like the reactants, right?
well, we are treating it as a reactant, right? We don't have to start thinking of it as heat or energy. We are just thinking of heat as a chemical now. So if heat is a chemical, like just all of these other chemicals that we just discussed, right?
Yeah.
If I give more heat, what would happen?
Wouldn't it just produce more heat?
It will favor the forward one. More of C will be.
Yeah, because it will try to produce
In an
more.
No, which one are we talking about?
The-
We're talking about the first one here.
Exothermic.
If I give more heat,
If it's in terms
Wouldn't
of
it
like,
try to also balance it out?
let's hear one at a time. Yes, Aditya?
if in terms of like reactants and products, then if you increase the heat on the reactant side, then heat will increase on the product side too.
Yes, but you are not thinking about it like that. I understand you are thinking about heat as a form of energy.
Yeah.
We want to apply this thing, this method, we want to treat heat as though it's as a reacting chemical.
Okay.
So don't think of it as heat energy on the energy on the both sides. So yes, Manan.
So if we add heat on the product side, the system will balance it out.
By doing what?
It will favor the N2 plus 3 actually.
Right, it will favor this side.
Yeah.
Because if we are taking the idea that okay, if heat is a reactant or a product, and here it's a product, and we add more of it,
Yeah, so
then the system would be driven this way. Isn't it when it was concentration, we said more of this means it goes this way,
Yeah.
and more of this means it goes that way?
Yeah.
So now for this one, what would happen if we give more heat?
It'll
It's
favor
going
the
to go
forward reaction.
forward because it needs to. Yeah.
Right.
Now what about the other side? If we decide to give this one less heat, a lot, make it colder,
It will be.
So it won't absorb as much heat, so it will favor A plus
right? Again, heat, it would try to go in a way, if you are not giving that much heat, it would try to go in a way to oppose that reactant.
Right.
It will favor
So it's
forward.
going to favor the
Then it's
forward
going to go this way.
reaction,
If it's not getting much reactant and you make it low, heat the reactant, then it would behave by coming this way.
Yeah.
So a couple of steps. First of all, when we see this, we have to know that heat goes on this side.
Plus heat.
When we see this,
Heat
we have
goes
to
on
know
the
that
other
heat
side.
goes on the other side. And then we imagine that if you have heat and you give more heat, the system will try to get rid of heat. And if you have heat as a product and you give more heat, the system will try to get rid of heat and come this way. On the other hand, if you have heat on one side and you make the temperature low, the system will go to the side that produces the heat, which could be whichever side. Okay, so this is the application. Our chemistry guide says to apply Le Chatelier's principle.
Okay.
Now, that's all we're doing here. We are understanding what the principle is. We applied it for concentration, and now we're applying it for exothermic and endothermic reactions, which is heat. We also look to apply it for pressure, but before we go on to apply it for pressure, we would take a worksheet now here with a few questions, and I want to come around and then work through that sheet and make sure you guys get this concept. Now I'm going to give you guys information one at a time. So for the first one, you know this minus delta H, and so for that first one, suppose we take the temperature from a certain point and we increase the temperature.
Yeah.
I want you to predict which direction the equilibrium would move in. And we have made the temperature go higher. What would happen? What is your prediction? So once you have it written out, let me come around and have a look. If you don't want to say heat will move, you want to say that the equilibrium will shift towards
Something.
the reactants. Equilibrium will shift towards the reactants. And this is a very, very good way. I mean, first of all, we did it with concentration. Let's go back and just talk concentration a little bit now. Suppose I increase the concentration of I2. What would happen to the equilibrium? How would it go?
Forward.
We'll go forward. Suppose I decrease the concentration of 2HI.
That would also go
Forward.
That will also go forward. If I increase the concentration of HI.
Go towards the reactor.
Right. So you notice something. People, very quickly, when we deal with this thing with concentration, no problem. That is why the idea has come up. Instead of talking about Advitya, about energy barrier and exothermic and endothermic and all of that, to come up with this strategy to just say, okay, we see the negative sign, let's put heat as a product. And once we're putting heat as a product, if somebody gives more heat, then it would go this way. If somebody gives less heat, it would go that way.
Concentrate.
And once we practice with it like that, the exam is not going to ask us to give any long essay with a reaction, with a reaction profile and lots of explanations. It's going to ask us about things like this. Yes.
Will they tell us whether it's exothermic and endothermic,
Well-
or do we have to know?
Well, they wouldn't use the word exothermic and endothermic. They'll give you this.
Okay.
And then this strategy now, so never are you going to see them put heat as a product, because that's not true. But you'll see hundreds of videos on YouTube where people are explaining and putting heat on this side and heat on this side and talking about it like it's some kind of scientific fact. That heat could be treated as a product or reactant. It can't. It's just a way for students to predict and get their questions correct. Okay? So it works really nicely with concentration. In fact, it's a well-established scientific concept with concentration. If you put more reacting particles of these, they will bump in together more and then they will go that way. Okay? But reasoning it out or thinking about it when you put heat on either side is sometimes difficult to. And this then just becomes something to help us get the question correct. Temperature is coming low this time.
Okay, wait. So, set temperature is okay, yeah.
So where will the equilibrium shift?
It will still
Forward.
shift.
Forward.
No, why would it be forward? Why would it be forward?
Right?
Heat is not on the reactant side.
So, see, heat.
Okay, wait. Heat, negative delta H means
Plus heat.
we are going
Right,
to
so
put.
plus heat. There's heat there. And so when there's a decrease in heat, it would still
So
move
therefore-
towards the reactants.
Yeah.
If we make the heat become less now, what will the system try to do?
Still like shift towards
Forward.
the reactants. Right?
Forward.
How can it be forward?
I'm hearing forward. Let me go around. I'm hearing forward. I'm hearing what?
See, so I'm confused
I want-
between
I
whether
don't
it go to
know
the
why
reactants
it's
or will it stay equilibrium.
Exactly.
It can't go forward.
Why
How can it go
forward?
forward? I don't
No,
know.
Okay,
because there's
that's
already-
all right. That's
I want
fine.
to know why is it forward? Like why?
Okay.
No, see, there's already heat present as a product.
Yeah, but like,
Right? So usually when that happens and there's a decrease in temperature there, so the equilibrium would shift towards the reactants to balance everything out. So I don't understand why the...
I know what you think.
so there's a difference in temperature everywhere.
Okay, now let's go back over it again then. Let's take out heat from here. Right? Let's take out heat from there. And suppose I increase the concentration of this, what would happen?
Reverse.
Reverse.
Right. Suppose I decrease the concentration of this, what would happen?
Forward.
Right, it will move forward.
Yeah.
Now, if I decrease the amount of heat in the system, where would it go? Because when I decrease this, the system went to fill this back.
Yeah.
This molecule, right? Now if I'm treating heat as a molecule and I say I decrease the amount of heat energy, which is a low temperature, What would the system
Wait,
do?
so is the heat decreasing over there or near the reactor?
Well, the heat is throughout the system,
No, sir.
right?
I mean like.
So it's forward, right?
Wait, I want to.
It is forward.
I just,
Oh, it is forward. Now, here's the thing. Yes, Siri, go ahead.
I just want to know where the heat is decreasing. Is it decreasing in like the product side or like the reactant side? Because if you
Yeah.
get
Well, this is the whole thing.
Totally.
You guys are having a problem. You're having a problem seeing heat as a chemical.
Yeah.
Somehow your brain is rejecting that, right? Because you can't see heat as a chemical. You want to see it in some other way. Because when we're saying this is a chemical and you accept and you associate ammonia as a chemical, less ammonia, the system tries to fill up the ammonia. So now heat is a chemical. If I say less heat, wouldn't the system try to replace and give more heat?
You can remove heat wherever there's heat.
But you've put heat and you are mentally trying to process it as a chemical.
Right.
Okay?
Yeah.
So therefore that's why it does
So the
that.
heat as a product in this case would decrease, right? Okay, yeah, then it will move forward.
No, the heat as a product is there. You
Yeah.
have decreased heat in the system,
Okay.
and the principle says that the system will behave to try to do opposite of what you are doing. So if you are creating low energy in the system, low kinetic energy, right? The system will try to increase and release as much heat energy as possible to do the opposite. On the other hand, if you decided to increase temperature again, what will be happening here now?
It will
Reversal.
It will try to go to the side that takes up energy from the surroundings. Okay, which is this side. Alright. So we have two examples. Yeah, yes.
If altogether you reduce the heat, won't the reaction just stay in equilibrium?
If altogether you reduce.
Yeah, altogether you just reduce it.
Well, to answer that, we'll have to go for something else. Alright? We'll have to go for something else because the reaction would not stay in equilibrium, because the thing about it is, one side, you are thinking the reaction would stay in equilibrium. Why are you saying that? Isn't it like if I said, Aditya, that if I increase this, you get more of this?
No.
When I increase this constant, forgetting about heat, if I increase ammonia, wouldn't you get more things on this side happening?
Yeah.
If I increase things on this side.
Yeah.
So now I tell you, forget about any analysis and just treat heat as it's a chemical. So when I say I'm giving more of this chemical, I usually wouldn't say more heat, I would say more temperature, higher temperature. Higher temperature means higher heat. So then in your brain you would say higher temperature means I'm increasing the concentration of this chemical, system goes this way. Lower temperature means I'm really decreasing the concentration of this chemical,
Oh, okay.
system
So then
comes.
just fill up
So
that.
that's what I was asking you. Like, are you reducing like the temperature of?
So low temperature means in terms of this chemical heat, low temperature means you're lowering its
Okay, yeah, I
concentration.
got that.
Lord.
High temperature means you're increasing its concentration. So once you treat it like that, I think then that would be better.
Yes, sir. I got it.
Alright, so let's try one more now from the next batch, which is 4 and 5, right? 4 and 5 are two endothermic reactions. And what did I say we were doing with heat or temperature?
Considering it as a chemical.
What did I say at the beginning? It's lower.
Decrease the temperature.
Right. So one thing that I realized will help you guys is if it's in place of temperature in your mind, you immediately just think of it as heat. Which is really going to be temperature in any question. They won't say heat, right?
Yeah.
But because heat is, remember which side will we put on heat on here now? Because it's
The reactant side.
heat is a reactant, and we have lowered the amount of heat, right?
Yes.
So where will the system go?
Reverse.
It'll go reverse. And it's not to overthink it, it's just to treat it like that. And you will always get the questions correct on exothermic and endothermic reactions with temperature. So for the same thing now, what about if we increase the temperature,
You go forward.
right? Then it will try to use, again, temperature. What another problem I notice is that we're saying temperature is the word, but then we're writing heat as the substance. So we also have to translate increased temperature to mean increase what?
Increase heat.
Increase heat. And decrease temperature to mean?
Decrease heat.
And then once we see this, what do we mean? Exothermic. So what side will heat belong to?
Product.
And once we see a positive,
Reactant.
Reactant.
right. So this what I just explained here. On if you guys want someone to go over it, not me. I've recorded this, but there's a very nice video on YouTube from Professor Dave Explains. You guys have ever watched anything from
Yes.
Professor Dave?
Yes.
Very nice YouTube channel. He goes over this very same concept because it's worldwide accepted that this is the way that students must learn about the effect of temperature on exothermic and endothermic
With the help
reactions.
of heat.
Right? To start thinking of heat as though it's a product or a reactant, and translating exothermic negative into heat on this side and endothermic as heat on this side. Okay, so that's one of the things that we want to fully understand. Whatever I shared on the FET simulations and all of that, I gave you guys that also. Do you think all of those would matter when the question just says, look, here's the reaction and we have increased the temperature. How would the equilibrium go?
It would move towards the reactant.
Alright, let's see it again, Siri.
Yeah.
If this is here, where will I put heat?
On the product side.
Right.
So when you increase the temperature, you basically increase heat. So then it will move towards the reactants.
Correct.
Okay.
Okay, so that you just go through that a few times, and it's like you're learning a language in the sense. First of all, this symbol means something. It tells you which side to put heat on, and then you have to think about this as heat and temperature as synonyms. Okay, because they mean the same thing. Higher temperature means higher heat, and then you just use some reasoning there, and you say, well, it could shift towards this side.
You teach us that temperature and heat are different things.
Temperature and heat
Oh,
are
yeah.
different things. Yes, correct. That's a very good point, I know. I taught you guys that temperature and heat are different things. But for solving this, for cracking these questions, as we say in the exam, you treat them as the same thing. Now, the idea, this is not something that I created. This is something that is created by chemistry teachers and textbooks all over the world. In the IB chemistry guide, they say students must apply Le Chatelier's principle to predict the effects of temperature, changes in temperature on exothermic and endothermic reactions. And that's what we just did. We took Le Chatelier's principle and we applied it. That's why I give you guys reference to Professor Dave video, because it's not just from me. You can go watch Professor Dave. You see in our book, it's there. Any chemistry, if you go on ChatGPT and you type in Le Chatelier's principle, exothermic and endothermic reactions, it will tell you the same thing. Actually, I did it.